Here is another question that I want to find a combinatorial proof, right? So prove that summation, that's identity, right? Summation k is equal to 1 to n, k into n choose k whole square is equal to n times 2n minus 1 choose n minus 1. So summation k is equal to 1 to n, k times n choose k whole square is equal to n times 2n minus 1 choose n minus 1. Of course, you can find an algebraic proof, and I would say that you can try to find an algebraic proof. It's going to be a little difficult, I think, but still you can find it. But it's going to be a little cumbersome to work out with this thing. But try it and try to find out why this must be equal. But then we want to find a combinatorial proof. So what is going to be our combinatorial proof? So think about finding a proof for yourself, and after spending some time, you come back here and then continue. Okay, I recommend that you think about it, because unless you think about this, it is going to be difficult to solve questions, because the subject of combinatorics is such that, you will see lots of problems. Each of them, the solution is kind of easy once you see it, but till you see it, coming up with the idea, right, how to frame this, right, it's going to be uh, tricky. You need to strike the idea in your mind before you can answer. It's not like a standard procedure, because each question has a slightly different flavor, which affects the way you have to think. So you need to develop a habit of thinking on this. So, and that is why I am asking repeatedly again and again that you uh, think on this before you proceed. So what is the combinatorial proof I am going to give you? Here is it. So what is on the right hand side? Okay, I have n and 2n minus 1 choose n minus 1. So I can immediately see that 2n minus 1 choose n minus 1 is choosing n minus 1 members from a 2n minus 1 element set, right? So basically forming an n minus 1 element subset of a 2n minus 1 element set. Now I am going to multiply that with n, which means that there is some choice involved, right? By our product rule, there was some choice of n persons, right? N distinct persons we were able to choose, and that is independent of the choice of the n minus 1 guys from the 2n minus 1 guys. So what I'm going to do is the following. Okay, I'm going to say that there are, let us say men and women, or boys and girls. Okay, maybe you can put boys and girls. And there are, let's say, n boys and there are n girls. Okay. So we have 2n persons here, n boys and n girls. Now from this, I want to form a, let us say, a club or a committee, whatever you want to call it. So I want to form a club with, let us say, n persons. Okay, I want to select a club with n people inside, and I want to make sure that the club has a, let's say, a president, and the president is a lady. It's a girl. Okay, they usually do a better job, right, as president than the boys. So therefore, we will choose a lady president, and then we will have remaining members. So now we can see what is on the right side, right? Because from the n girls, I can choose one president for the club in n possible ways, right? So I have n possibilities to choose the president, right? President. Now, my requirement for the club was that the president must be a girl, right? But then the remaining there is no condition. So therefore, I have once I choose the president, the remaining members, president is already a member. So remaining n-1 members I have to choose, right? But the n-1 can be any of the people. So therefore, I can choose any of the n-1 person from the two n-1 remaining people, except for this one girl. There is n boys and n-1 girls. So out of the two n-1 persons, I can choose n-1 members, including the empty set. Right? Only there is a president, nobody else, right? That is allowed, right? No, sorry, I my mistake. So yeah, so I choose the president and I select n-1 members depending on what is n, right? Yeah, unless n is 1, right? It's not empty. So you choose n-1 element subset of the 2n-1 set. So you select these guys in 2n-1, choose n-1 possible ways, and then since the choices of the president and the remaining n-1 guys were independent, right? The number of choices were independent. Choices are not independent, right? We could multiply them. So I get n into 2n-1 choose n-1. Now the claim is that the left-hand side counts precisely the same thing. So why does the left-hand side counts precisely the same thing? So what happens on the left-hand side? I have summation k is equal to 1 to n, k into n choose k whole square. Okay. So let me count this, the president forming club forming business in a slightly different way. So how I am going to count this? So first I will form the club by selecting k girls from the n possible candidates, right? So I choose k girls from the n possible girls. So I say that, okay, these girls are going to be the members. Okay. Now, once I choose the k girls, I will select one of them to be the president because I want a girl to be the president. So therefore, out of the k girls, I have exactly k choices to make one of them as the president, right? So I choose k girls and then select one of them to be president. And this is independent, right? So I choose the k girl first and then independently, whichever k girls I choose, one of the k I can choose. So there are k choices for that. So k into n choose k ways. I can choose the n girls to be in the club and then take select a president. So k into n choose k. Then once I choose the k members for the lady members, I select the remaining n minus k boys from the n boys, right? So from the remaining n boys, I need to select n minus k boys. But instead of selecting the n minus k boys to be in the club, I select the k guys who are not going to be in the club and throw them out, right? That is the same choice I'm making, right? So I make the choice of k members who are not going to be in the club, throw them out, and then select the remaining n minus k guys to be in the club. So this is a way I can form a club with n minus k boys and k girls and one of them as the president. But this can be any of the case, right? K can be 1, k can be 2, etc. K can be n. And each of them give distinct clubs. So therefore, the number of ways to form the club is summation n choose k into k into n choose k, which is summation k into n choose k whole square. Okay, I should erase this, right? So, but now this is all possible ways it can happen that there is a lady president and there is the remaining members were chosen. And, all of them appear here. So therefore, these two quantities must be equal. So that is why we have the equality. This is equal to n into 2n minus 1 choose n minus 1. So what we counted on the right is precisely what we counted on the left. So therefore, they must be equal. So this is another combinatorial proof. Okay, I think I could have written it here. Now, so recall the special property that we observed from the Meru Prasara of Pingala, right? We saw this, right? This nice property. Not this one. Where was that? Yeah, I think I erased it. So we had this property, right? That the sum of these guys for this, right? Or sum of this entire guys will be this. Similarly, sum of any of this will be exactly this, right? So using this observation, we can write it in a formal way, right? I asked you to form it yourself. Maybe you have already done it, but if you have not done, here it is. That k choose k plus k plus 1 choose k plus etc. n choose k is equal to n plus 1 choose k plus 1, right? We just went one step bottom and one step to the right, right? That is what n plus 1 choose k plus 1. We can see it in the table now, right? In the triangle. We can see this pattern why this happens to be like this. So this is precisely the diagonal that we are looking at, and this is the off diagonal entry that we were showing, right? So so this property I want you to prove now combinatorially. Okay, come up with a combinatorial proof why this must be the case. So this is a homework for you. Okay, let me also write homework in case you want to see the lecture notes. So this is homework. Okay, now looking back to the anagrams of look, right? I asked you to solve this yourself if you can. You must have already solved it. You can definitely use brute force to solve it, right? If nothing else works, you can just write down all the words that you can come up with and count it. So if you have counted it, you must have found the answer will be 12. Okay, so what is that number? So how did we find this? Okay, so maybe you can, maybe I would suggest that you try to find it out by whichever way that you prefer. Now I am going to use a different method. I am going to, or maybe not different, but a method as follows. So the reason we were not able to use the product rule was that now when we were having this LOOK, there were two O's, right? Now the two O's, when I choose, there will be several orders that I make when I put them in different permutations, but some of them could lead out to be the same, right? So which says that the choices were not really independent, right? The choice of one of the O's was interfering with the choice of the other because the other comes here or this one comes here is the same exactly. So because of that lack of independence, we could not directly use the product rule. If you want to use the product rule directly, we should be able to bring in more independence. Now, how can you bring independence? So you can bring independence by saying that the O's are actually different. Okay. So I will say that I will have the O's, but LOOK. But one of them is O number 1 and the other one is O number 2. Now, if I mark the O1 with always O1, O dash or whatever, and the second one with O2 always, then the anagrams are going to be exactly 4 factorial, right? Because all permutations are going to be different. Because if I put, for example, LOOK with O2 here and O1 here, this new labeled O, LOOK is different from this labeled yellow. Okay, because this is the first O and this is the second O, but where is the second O which is coming first and the first O coming second, right? So therefore, I can count now using product rule. So there is going to be 4 factorial, which is equal to 24 different words with the new O's, right? The labeled O's. But now, what we observe is that because, when we remove the labels, this one and this one counts to be the same, right? They give the same number, right? Same word. So let us see how many overcounting we are going to do when I do this 4 factorial equal to 24. So we observe that once you fix the positions of the O's, right, the 4 different positions of the O's, let's say O appearing here, O1 and O2. If I swap their positions, it is not going to make any difference in the word, right? Because when they remove the label, they are going to be the same. Can you do anything else? I cannot move the O to somewhere else because that is going to create a different difficulty, right? It's going to be a different word. So, if I swap, there is no problem. So, when I swap, how many possibilities are there? Either 1 goes to 2 and 2 goes to 1 or the same thing, right? There is only 2 possibilities, right? So, therefore, there are exactly 2 ways to get this O1, O2 or O2, O1 by swapping them. And these are the only overcounting. So therefore, every word I counted exactly twice because O1, O2 was coming and O2, O1 was coming in. So O1 comes first and O2 comes second, or O2 comes first and O1 comes second. In the same positions, they lead to the same word. So therefore, I can use the division principle now to say that because I overcounted every word exactly twice, I can divide by 2. So 24 by 2, which is equal to 12. So there are 12 different numbers. And you can verify by finding the 12 different numbers. Now, okay, we found out the counting for LO. Okay. Now I give you a bigger word. Let's say Mississippi. Can you count the word Mississippi and its anagrams? Right? SSISSIPPI. Right? Mississippi. Now, I think once you get the idea of the other one, this is easy. So suppose I put labels to make sure that all the words are distinct, right? So I will put label, let's say I is occurring 1, 2, 3, 4 times. I will say I1, I2, I3 and I4. S is appearing 4 times, so S1, S2, S3 and S4. P is appearing 2 times, so I will put P1 and P2. Then M is appearing only 1, so I will not do anything. If you want fun, you can make it just M1, doesn't matter. And then I say that, okay, I take this, these are distinct words, distinct letters now. I take all possible permutations of this. I get words, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 words are there. So therefore 11 factorial permutations are there. Then I observe that, okay, but whatever the permutation is given, the I's are occurring 4 times, right? But they were all 4 different I's because I put labels. Now if I switch the position of 2 of the I's, it does not make any difference to the word. In fact, if I switch the positions of any of these I's between themselves, it doesn't make. In fact, if I permute all the I's within their position, right? So each of them has a fixed position in the word that we created, right? There are 11. I will not draw all the 11. So I will just mark the special positions where I was occurring in the word, maybe, right? It was occurring here, maybe, and here, and maybe here. Okay. So the I was appearing here, I1, I2, I3, I4 maybe, right? Now, I don't change the positions of in the word, but between the I1, I2, I3, I4, I can permute them any way I want, right? So the 4 i's can be permuted in 4 factorial different ways, right? The 2 o's we could permute in 2 different ways, which is actually 2 factorial ways. So the 4 i's I can permute in 4 factorial different ways, and each of the 4 factorial permutations, right, that I obtained by labeling them, we're all going to give the same unlabeled word, right? Where i's are all identical, I will get the same word. So I have to divide this 11 factorial by 4 factorial to compensate the fact that I overcounted all the permutations of i's in 24 different ways, right? So I overcounted them 4 factorial many ways. Similarly, there are 4 different s's, so I can apply the same rule. So I can use again division rule to say that, okay, once I unlabel s, all these 4 factorial will give the same word. So 24 of them will give the same. So I can divide by 4 factorial again. Then I have 2 different p's. So I can divide by 2 factorial different ways. There is only one m. So I can divide by 1 factorial if you want. But we didn't overcount there. So therefore, I say that 11 factorial by 4 factorial into 4 factorial into 4 factorial. Different permutations or anagrams of the word Mississippi are there. Now it is very interesting to see that, 11 factorial can be divided by 4 factorial 2 times, 2 factorial once, and still we will get an integer, right? Because we are counting, right? Counting things, right? Number of anagrams. It must be integer. There is no other possibility. So, anyway, that is just a remark. So this leads us to something called multinomial coefficient. So what we were looking at now, okay? We use division principle and multiplication principle only, but we can now come with a slightly more general, slightly refined tool, but more basic, still basic. So this is called multinomial coefficient. So what is the multinomial coefficient? Let S be a multiset consisting of n1 objects of type 1, like we had here 4 objects of type I, right? I, 4 of them. They are all identical. 4 different s's, 2 different p's, etc. Right? N1 objects of type 1, N2 objects of type 2, N3 objects of type 3, etc. Nk objects of type k. And N1 plus N2 plus N3 plus etc. Nk is equal to some number n, which is the set S we are looking at. So S is the multiset. It has cardinality N1 plus N2 plus etc. Nk, which I call n. And these n elements, right? There are these repetitions, N1 of particular one type, N2 of another type, etc. Nk of another type. Then the number of linear arrangements or permutations of all of its elements, right? All of these elements, because they are identical elements are there, right? Is precisely n factorial by n1 factorial into n2 factorial into n3 factorial into etc. Nk factorial. So this is called the multinomial theorem. Okay? I mean, not sorry. This is this is called multinomial coefficient, and we want to see why this is precisely this. We already saw the proof in some sense, right? We argued it, but let us make it little more formal. Okay. So here is the proof. So first consider each element to be distinct. Okay. So by giving labels. Okay. So we start with the multi-set, but now the multi-set has same element appearing many times, right? The type 1 objects, O1, O2, etc. I mean, like let's say OK are there. So O1 is appearing, let's say, number of times. O2 is appearing number of times. These are all objects or elements of the set. And OK is appearing n k times, right? So what I am going to do is that I will make O1 to be O1 dash, O2 dash, etc. No, O1 dash. I mean O1, O1 1, O1 2, O1 3, etc. O1 n1. Similarly, OI will be OI1, OI2, etc. OI ni. Okay, I am putting more labels to make them all distinct, right? Labeled objects now. So now, since I have n objects in total. Once I do the labeling, I get exactly n different objects, right? The new labeled objects are right. So now I look at the permutations of them. So how many are there? N factorial permutations are there. After this, I do the unlabeling. So what I do is that I unlabel the n1 objects of type 1. So once I do this, what happens? Okay. So in general, what happens is that if I if I unlabel, so here O1 is 3, O1, O1 1, O1 3, and O1 2 are there. So there are 3 objects of type O1. So what I do is that when I unlabel these 3 numbers, when I unlabel these 3, what happens is that they, the different things will become the same, right? So there were 3 of these objects. So 3 factorial different ways I can permute, and each of them will give the different objects in the labeled fashion. But once you unlabel, each of these 3 factorial, right, will be corresponding to the same set, we were looking at. So therefore, that is overcounting, right? So similarly, OI be the type I object. We have labeled them as OI1, OI2, etc., OINI to make them distinct. Now, among the n factorial permutations, let us fix one of the permutations. Okay. Once you fix the permutation, consider the ni positions where the OIs appear. That is what we looked at here, right? The 3 positions where O1 was appearing. And then between these fixed positions, I will not change the positions, but I can permute the copies of OI, right? OI1, OI2, etc. OI, Ni were there. These guys, I can permute them between themselves. They will all lead to the same ordering that we were looking at, because when we were looking at the unlabeled ordering, right? So they were contributing how many times? Ni factorial permutations were giving the same thing. So therefore, the overcounting they permuted and a multiple of Ni factorial. So therefore, I have to discount this or by using the division principle by dividing by Ni factorial. So since the in place arrangements of Ni copies of Y does not depend on that of the Nj copies of Oj, right? So I look at the Ni positions, rearrange them. I look at the Nj positions of the other objects, right? Not these objects, and then rearrange them there. That doesn't affect here, right? For example, when we were looking at this, we were looking at copies of O1, O1, 1, O1, 2, O1, 3. So even though I permute them between themselves, no matter what, right? I will say that this goes here now, right? And then this guy who was here will go here, and then this guy who was here comes back here, right? Now this rearrangement does not affect the rearrangement of, let's say O2, right? O2, there are 2 of them, right? O2, 1, no, 3 of them again, right? So O2, 1, O2, 3, and O2, 2, right? I can rearrange them independently because their positions are different. So therefore, these arrangements are independent. So therefore, these permutations, Ni factorial permutations, are all independent. So the total number of overcounting is n1 factorial for the first object, n2 factorial for the second object, and nk factorial for the last object. And they are independent, so I can multiply using the product rule. So product of n1 factorial, n2 factorial, etc., nk factorial is the total number of overcountings. So therefore, now I can say that since I have overcounted every object this many times, I can divide by the division rule. So therefore, I get n factorial by n1 factorial into n, etc., nk factorial. So that is how we prove this. Okay, so this is the multinomial coefficient.